So, one or two of you probably know my name. I've been around a long time, as you can see, and I've worked on lots of things, many of which will appear in this talk. I like to think of this talk as a prequel to Antoine's talk. Antoine has a paper jointly by us and by Pedro, is that right, isn't it? In the main disc program, and that's on, was it Wednesday or Thursday?
It's tomorrow.
Tomorrow, right. And so this is some of the work that underpins the thinking behind that talk. His talk is on a new consensus algorithm for blockchains and similar sorts of things. So I won't talk at length about that here for obvious reasons. What I will talk is about the general use of what I call stochastic certainty in decentralized systems and the associated verification methods, which seems appropriate to this workshop. If you look at the title slide here, what you will see is the right-hand half of a familiar bell-shaped curve for the normal distribution, with one or two familiar points on it at the left. So as you can see, obviously the normal distribution is 50% likely to be to the left and 50% likely to be to the right of the mean. We're only interested in the bit to the right of the mean because we're only interested in having too much bad behavior amongst the agents in the network rather than too much good behavior. So we're only interested in that half of it, although of course any part of it can happen. We're interested in some fairly extreme regions of it. The bits you see on the left of that screen represent 1 sigma, 2 sigma, sigma of course being the standard deviation of the normal distribution. As we see here, a typical sort of confidence interval people use with the normal distribution is about sort of the 95% chance of being within 2 sigma of the mean. We, however, for a reason that will become apparent in a few minutes, are going to go way out to the right-hand side of this overhead and be in the region of 8 sigma or 9 sigma, which takes you out into the region of about 10 to the minus 18 probability, or as I've done a quick conversion here, to 10 to the minus 18%, which is not very likely at all. And that's the whole point, because what I want to do is to move from stochastic systems to effective certainty. So this is part of my program that I call Reinventing the Blockchain, because like many computer scientists, I would have seen blockchain maybe 10 years ago for the first time, and people persuaded me that my talents were such that I should start to work on it, and I immediately decided that in many ways it was a little bit naive as a construction, so I wanted to do better. So I wanted to build upon the basic idea of a blockchain to create a more efficient and resilient structure. And again, obviously, I'm looking at decentralized communities for blockchains. There's not much point in building a blockchain if you're not decentralized. There's not much point in building a blockchain if everybody trusts everybody else. So clearly, one always trying to build trust and quite a high degree of sequentiality via a blockchain. And I started off seeing blockchain, because of my origins in concurrency theory, I started seeing blockchain as a very nice model of concurrency in the sense that, albeit at quite a high execution cost, it ironed out a lot of the uncertainties arising from the natural models of concurrency that we were all used to. And a thesis that I developed quite early on in this work was that I wanted to be a bit more scientific about the way I treated the necessary possibility of having badly behaved agents in these systems. But I wanted to do it safely, and I want to be able to take advantage in a natural way when there is actually less bad behavior than you allow for. So I'm going to allow for a maximum amount of bad behavior in my network, like everybody else. But I want to try to take advantage when that bad behavior doesn't appear. But obviously I want to do so safely. I don't want, even though I've been optimistic, I don't want the bad guys, by actually behaving badly, to have any lasting effect on the chain. I don't want bad decisions to be made. So, in some sense, I see blockchain and similar sorts of structures as being magical tools for turning a lot of unknown trusted behavior, in the sense that I don't know whether I can trust it or not, into something which is purely angelic and follows the rules. So what we need to do is to understand, construct and verify these decentralized systems in the presence of assumed malevolence, an assumed degree of malevolence. Now, of course, you can build all sorts of models of malevolence, but what everybody does, because it is sort of symmetric and convenient, and of course I do the same, but obviously one has to allow for doing things differently in practice, is to assume that all agents are potentially malevolent or Byzantine. Byzantine, of course, means that they can do anything they like. There are two classic models you could take of a malevolent agent. Either they could do anything they want to, obviously within the bounds of what cryptographic structures they know and what keys they know. Alternatively, we could just have ones that can stop, that can put their feet down, or as I call it, playing possum. But with overall limits on how many. I mean, that is a classical approach that people take in blockchain. So following my agenda in this format had me baffled for a long time, although obviously from my very early days in using CSP back in 1978-79, which is when I first started to work on it, I was very, very used to building models in CSP of systems that had bad components in and modeling them. Those were some of the very first examples I ever worked on. But then I discovered three techniques which helped us to overcome the barrier of how to deal with a maximum amount of bad behavior while taking advantage of it when they actually behave well. And these are stochastic proof, which is the main topic of this talk, the consensus machine, which is very important to Antoine's talk, and the handover protocol, which is also important to Antoine's talk. But I'll talk about the two of these things in, sort of roughly in this talk. And then, of course, my decentralized model mapped perfectly into my old friends, CSP and FDR. And indeed, as we'll see later on, it required them to justify some of the abstractions that I had made, and therefore it was nice as somebody whose origins were in verification to find that I could go back to my old friendly tools and friendly abstractions. So let's have a look at the idea of stochastic proof. I mean, it may sound from this title of this talk as though I'm going to talk about things that are uncertain, but really what I'm trying to do is to make things so likely that I can treat them as certain. I'm going to pick collections of agents using an unbiasable random process. I'm going to think that my choice of agents is made by some perfect, fair, probabilistic choice from the available collection of agents, such that we know, and I'll go back over that point in a minute, that a chosen proportion of them are good, with a certainty so high that we're prepared to ignore the risk. And I have picked in most of my own writings on this topic, though we'll see us varying in this talk itself, the chance of a single thing going wrong is about 10 to the minus 18. And the tolerance must be based upon two things. First of all, how many selections I'm going to make in a reasonable approximation to all the time. So I might have a year, 100 years or something like that as my time. And I've got a certain rate over time of it being made, and so let's suppose I'm interested in the first billion blocks of a blockchain, which is a pretty good number if you look at the chains that are out there. I need epsilon times S to be negligible. So that's why I picked up on this. I've got a billion blocks, and epsilon equals, and I've got one event per block, then obviously that means to say the chance of anything ever going wrong is very, very slightly less than 10 to the minus 9. So what do I want to prove? I might want to prove that there's one good agent in the collection. I might want to prove there's 51% good, or I might want to prove there's 67% good. We'll see some concrete figures for that in a minute. And then I simply assume this in analysis of behavior. So in other words, whenever I make a selection of agents, either implicitly or explicitly, what I do is I then assume that sufficient of them are good as an input to my algorithm that will make it work. I notice that the Byzantine agreement is just a special case of stochastic proof based upon an assumption, and let's have a look at that in a moment. So, well, first of all, I'm going back over this multiplier. So the limits for stochastic certainty depend crucially upon the number of tests. And if one committee is selected for all time, there's only ever one selection made, and so perhaps I can then assume that the tolerance is 10 to the minus 9, if that's the maximum chance I'm going to allow over all time. And for Bitcoin hash puzzles, there are about 2 to the power of 95 per annum, which I worked out and found some very interesting analogies for. For example, I did work out that the number of hashes Bitcoin needs to do to work out a single block is, if I remember rightly, roughly speaking, equal to the distance to the Andromeda Galaxy in centimeters, and things like that. And 2 to the 95 is quite close to the number of grains of sands it would take to make up the Earth, that sort of thing. So anyway, my central case that I'll be concentrating on here, though clearly you could apply this much more broadly, is blockchain algorithms where there's the order of one test per block. And I'll very often be testing committees, by which I mean to say groups of nodes to whom some decision is delegated. And I want to rely for practical purposes on things never going wrong. There are all sorts of things that we assume will never go wrong in practice, but have higher probabilities than this, like not getting struck by lightning, or a plane not crashing, and that sort of thing. They all have far higher probabilities than 10 to the minus 9. So let's look again at Byzantine. Yeah.
So this term stochastic proof refers to the set of assumptions you're making?
That's right, yes.
Yeah, okay.
That's right, yeah. So let's now look again at Byzantine agreement, because most people know Byzantine agreement. Byzantine agreement is a way of making decisions in blockchains and similar systems where you have to assume that 2/3 or slightly more than 2/3 of your agents are good. Because without that, and with the sort of standard models of behavior and of interaction, the bad guys might force a bad decision or might force no decision. So you need this level of goodness in order to first of all have liveness, in other words that the decision will come out, and secondly to force the fact that you can never get ambiguity. So for example, you can never get a fork in a blockchain. People usually assume that 2/3 of their agents in blockchains are good because they want to use Byzantine agreement. However, this is not something we can actually force. It has to be an assumption. So we have to examine the question of what assumption this is based on. So it's much more realistic to do some sort of analysis of a typical person who might come along and join our collective, and we might assess based upon whatever, that they're, say, 2/3 likely, or 3/4 likely, or 50% likely to be reliably good. But if you actually analyze it, you find that if we have, if we actually chose P to be 2/3, in other words, the probability of a given agent being good is 2/3, then no matter how big the collection is, as long as it's reasonably big, And because of that bell-shaped curve that I showed you earlier on, and the central limit theorem of probability, it actually tells you that there's only a 50% chance that less than 2/3 will be, sorry, more than 2/3 will be good, right? It's just a most elementary derivation of standard probability theory. So if we are going to demand stochastic certainty, then we want it to be certain at, say, the 2 to the minus 9 level, because we're only going to make one selection of agents. And if you actually do the sums, I've done a lot of these sums, if you put p equals 3/4, in other words, it's only 1/4 likely that an agent will be bad, then you need actually, we need actually to pick 333 of them. If there are 1,000 altogether, if we've got 1,000 agents, I need to pick 333 of them to ensure that 2/3 of them are good, or something like that. Yes, that's right. And that goes down to, I need p equals 0.9, and there's only 10% chance of being bad if the population is 40. The conclusions there are that assumptions about unknown populations are inherently stochastic, whether you admit it or not. So I argue that every blockchain that was ever built, certainly every blockchain that was built around something like Byzantine agreement, has an implicit stochastic assumption that was not actually very well analysed in most cases. And if you think about it, actual Bitcoin mining, I've never bought a Bitcoin in my life, may I add. Neither have I ever advised anybody to buy one. If you actually look at the Bitcoin mining population, you find that it's incredibly clustered. Sometimes as much as 70% of all Bitcoin mining has been owned by a single person, which is just ridiculous if you think about it. And typically these days, most of the mining is in the hands of a few people who typically own about 20% each. And that turns out to be quite a crucial number. Well, actually, it's not crucial, but it's quite crucial in the sense of a statistic I like to quote, which is that if you control 20% of all Bitcoin mining, and you do so covertly, in other words, you're not telling anybody you're doing this, right? You just built it quiet on the quiet, then you could destroy the Bitcoin finality model, that's to say when transactions are said to become final and actionable, which is, I think, having 7 blocks on top of the one where the transaction is, on average in a week. And again, all of that's going to appear in my book. There's a very precise definition that clustering, as everybody knows in this sort of world, is very harmful. So what I'm going to do is I'm going to use committees for individual algorithms via bulletproof random beacons. I say bulletproof here because we're absolutely dependent here on the fairness of our choice of these committees. And this can be done directly. In other words, I might choose a particular committee from a specific random beacon, or I might rely upon some other choice that somebody has made for a different purpose. For example, picking the last n block creators in a blockchain or something like that. And if you do that, then I like to concentrate on the 3 different sizes of committee that you can pick. A small committee is one which is guaranteed to have some small constant, like 1 or 2 good members. It could be an intermediate committee, which is guaranteed to have half good. Or it could be a large committee, guaranteed to have 2/3 good, as in Byzantine agreement. And we'll see some figures for this in a minute. Here they are. Well, I made up this table here. And if you look along the bottom, we see the size of the sample which has been picked, been chosen fairly using my fair random oracle. And I'm now allowing a subset to be chosen by the demons. I will see why demonically. And I ask, so what can they force? So if the sample has size, say, 50, then if the probability of a single agent being bad is only 0.05, in other words, 1/20th, then if I've got 7, then and this is the smallest subset stochastically guaranteed to have at least one good member. So 17 is the smallest subset guaranteed to have one good member. If the bad guy picked 17 of them, there'll still be one good member. And the point is now that is less than a third. That's actually, well, it actually is less than a third if you actually look at the rounding errors. Less than a third of 50. And so I can there run Byzantine agreement. If I want an intermediate size committee, I could do so if I had a probability p is 0.1, and if I had probability 1/3, or even very slightly bigger, I could guarantee there was at least one or two good members. But we see how this table, if you like, allows us to calculate sizes of committee, and of course, this is just done using, well, actually I've done this in two ways. I've done this once using an actual computer implementation of the binomial distribution function, and I've done it using the central limit theorem. And they do sometimes produce very different results, but of course they're always very similar. So why demonically? This is the slide I like. I wrote this slide here, and I realized that what I was seeing here was a demonstration of something I personally have worked on in concurrency theory for the last 25 years, which is to try to understand the difference between probabilistic non-determinism, when there's some fair arbiter making a choice, and demonic or non-deterministic choice. The point is, of course, that the choices are being made of which of the subset are being made effectively by the bad guys, because they can choose to behave badly or well for themselves, and they can choose whether or not, and they can choose to do it faster or slower than the good guys. They can block the good guys, potentially. So the ones that the ones that people see first are the bad ones. And so these choices are not entirely, but often very substantially in the hands of the bad guys. And one of the worst things a bad guy can do is to play possum. Play possum is an English expression meaning to play it being dead even though you're not. And so I found this cartoon on the internet last night, which is well, first of all, I found a genuine photograph of a real possum playing dead, and that was horrible. And so I decided not to use that one. So I found this nice cartoon instead. And if you look at the cartoon carefully, you'll see that this cartoon possum, it's got a notice on his tail that says, "Do not disturb, I'm dead," misspelled, maybe. One of the worst things you have to deal with in modelling this sort of behaviour is understanding what havoc can be wrought by bad guys playing possum. And one of the worst things about playing possum, actually, from the point of view of the good guys, is that it's much harder to penalise than doing something which is demonstrably bad. So here are the examples from my own work. One of the first, I think, really significant idea I came up with, and something where you can find papers by our group, including Antoine, I think, is the idea of hooks in blockchains. We're all familiar, at least anybody who knows a blockchain is familiar with the idea that every block contains a hash pointer to its predecessor. That, of course, is something you can only create when you know the predecessor. And it means to say that from any block, there's only a unique passageway back to the genesis or initial block of a blockchain, and that if a block doesn't have a passageway back to the genesis block, then it's not a real block. Unfortunately, and this is something that's been recognized since long before I started to work in blockchain, that doesn't create a tree, it doesn't create a chain data structure, it creates a tree, a rooted, arbitrary branching tree. Because although each node can only have one ancestor, one direct ancestor, one parent, it can have as many children as it likes. A little bit like we humans who have two parents and as many children as we like, right? So one of the first challenges I was given when I started to work on this was to find a way of getting around that problem. That there's no, should we say, endogenous, there's no way actually within the blockchain itself in which you can tell whether or not there are multiple branches, and whether you are now on a true branch of the blockchain or on a fake branch of the blockchain that somebody has cloned on. Well, I found a way of doing that, which is effectively to add in the links that go forward as well. Of course, they're not put in directly, but they're put in a way that works in much the same way. In effect, what you do is you put in a public key into every block, and you use that public key, or rather the block creator uses that public key to add a pointer to a block quite a few steps down, which I call a hook. And by doing that and doing appropriate stochastic analysis, which is where all this fits in, you can verify that it is stochastically impossible to create a believable fork in a blockchain. And in fact, one of the reasons why I discovered the stochastic analysis was because I was desperate to find a way of properly analyzing the behavior of the potential evil behavior in hooks. There are many instances in classical consensus algorithms where you actually need something like stochastic analysis. If, for example, you've got a proof of stake blockchain or something like that, where you've got to have a number of different candidate blocks which are up for testing by the verifiers, you need to make sure that at least one of those is good. And how would you do that other than by picking, either implicitly or explicitly, one of these small committees I talked about on the previous slide? The two-level consensus algorithm, which Antoine is going to be talking about, basically what it does is it enables you to have not one decision procedure, but two for consensus. One that works on the assumption of not too much bad behavior. It's got enough to block bad decisions, but the bad people can block a good decision if they want to. In other words, it might either make a good decision or it might deadlock, or produce something which is behavioral equivalent to deadlock. Again, that's a familiar thing from my verification history. And you have the second level, which sort of picks up the pieces if that goes wrong. Coping with that ambiguity is what creates the need for a handover protocol, hence the picture of a handover there, where you have to hand over from the primary to the secondary. But Antoine will be talking about that. And actually, we have ways of creating a random number beacon, which we need for the reliable stochastic choice, again using various options here. And indeed also coping with various forms of reliable communication. So I think that Antoine's talk, if I remember rightly, will concentrate on one of these. There are other ones you could use as well, some of which may be worse, but certainly some of which are better than the one that he assumes. So that really finishes my introduction to stochastic proof, but what I want to do is briefly say how it interacts with perhaps your main interest, which is verification. So we've abstracted organized, decentralized behavior into things which we call consensus machines, where people move from one state to another by consensus. And they do this by communication by decentralized signals. In other words, they can either be sequential or they can be parallel. If they're sequential, they're themselves parallel, but they have this organized behavior. If they're in parallel, there are several of them communicating with each other. And the way we organize communication between them is by having a very carefully thought through and very non-deterministic version of shared variables. I actually developed the handover protocol, which is part of Antoine's talk. The original version of it I developed by running it through FDR, because I didn't actually know if my original proposal would work in a highly decentralized environment, but fortunately it did. And I have, for example, you can model these things either as a single consensus machine as a sequential model, as a sort of abstraction of its true parallel behavior, or you can build a version of it using a relatively small number of nodes. A separate piece of work, which I find quite interesting, is the fact that we actually managed to get to work a small model of a blockchain, really putting together blocks and developing as long as we could find innovative ways of modelling the huge potential range of data storage you would need in any such model. And of course, because of my own background, I did all of this in CSP and FDR, because that's what I'm good at. I would love to see other people coming in and looking, for example, at some of the stochastic modelling using some genuine probabilistic modelling tools. And I simply haven't got around to doing that yet, but I'm old. Let's have a look. So I'll just, before I finish, just talk about my book series that's coming up. When I started to work on blockchain, as I say, about 8 years ago, I started to write a paper which I call A Computer Scientist's View of the Blockchain. I never finished it because, like many such projects, it just grew and grew and grew as I understood more and more and more, and understood less and less and less how to say what I wanted to say. So the paper itself changed vastly in various editions that I wrote, never got published. But eventually it crystallized out into a series of 3 books, which I'm now writing. The first 2 is a solely authored book by me, and the other 2 books are probably going to be jointly authored books by me and Pedro Antonino, who is a co-worker of Antoine and myself in Oxford. And the first one is really about the blockchain and sort of the general principles of decentralized systems. The second one is going to be about interactions between that and the twin concepts of digital civilization. In other words, how can you do civilization and manage people's data better, and trusted computing. Because trusted computing is like blockchain. It's a way of basically manufacturing trust out of technology rather than expecting the actual people who are running it to be trustworthy. So both of these technologies have in common the idea that we don't want to trust the people who are running this technology for us. And of course there are other solutions to this, like homomorphic encryption and so on, but we will touch upon that. But the 2 main technologies we cover are first of all going to be blockchain, as in this book, and trusted computing in the second book. So we actually work with quite a few real experts in trusted computing, although I certainly don't count myself as that. Pedro is becoming one, but we work with other experts such as Sergeant Caption, who is in Zurich, where you're not allowed to have a laser pointer by all accounts. It's apparently illegal in Switzerland. We're also planning, but we haven't written very much, if anything, of a 3rd book, which is about the actual means of developing and verifying decentralized systems. So looking at all the sort of different techniques one can use for applying verification techniques and this sort of thing in this area. So that might be the most interesting book to this particular community. Anyway, that's, I think, is all. Thank you.
Thank you. So any questions? Maybe a few minutes.
I will say that if you look at our company website, and I'd maybe ask Antoine, he will tell you about a few papers on different aspects of this that we have published already, but there'll be far more in the book. And the book, by the way, I think I have promised to hand it over to the publishers, and I'm still optimistic I will make this, in the first week of 2026. And I'm told the publishers promised me faithfully that if I do this, then the book will appear in June, which I must say I find a bit disappointing.
So I do have a question.
Yes, go on then.
So you had a slide about the verification techniques, and it looks like you listed a few abstractions that you came up with. Yeah. And I mean, in my experience too, it's very crucial to come up with the right abstractions for verification.
Yes,
and
absolutely.
I was wondering
Always,
if you have
couldn't agree more.
Yeah, did you have any advice on how to do that?
I will tell you. I mean, I may seem to be very, very egotistical when I say this. That it was said a long time ago about FDR that it could verify absolutely anything as long as I was doing it. So for example, you're probably well aware, for example, that we came up with some we came up with some great models of cryptographic protocols in the 1990s, for example, which everybody then jumped on the back of, right? And to be honest, it's my colleagues who are now running a company called Cocotech, who developed the abstractions that allowed them to verify the, who allowed them to take the way that people develop embedded software using object-oriented techniques and converting them into a language which is effectively CSP for verification. And the great thing about that is, and I take no credit for this whatsoever, but it just shows the way in which verification thinking can really pay off. Which is that my colleagues, who are initially a guy called Guy Broadfoot, and then his daughter Philippa Broadfoot, who was my doctoral student, and another protege of mine called Tom Gibson Robinson, developed the technology which is developed by Cocotech, which used to be called the Coco system, and now it's called Populi, a purely randomly branded name, may I say, which effectively allows you to develop your model-based system as if you were an engineer developing in something like UML. And then it automatically abstracts from that the right models to do compositional verification. So the reason why that companies like ASML can verify millions of lines of code using this tool is not because the model checking suddenly becomes able to deal with such vast systems, but because they've used the right compositional verification techniques. And so I'm inclined to think that we in the verification community have developed a very large number of truly amazing techniques. It's just that I think often the verification techniques, and here I'm going to be slightly critical of ourselves, have been too focused upon developing our own techniques and the niceties of our own techniques, rather than going out and applying them. I've been to a few verification workshops, and because I haven't heard any other talks here yet, I don't know what it's going to be like here, where people are much more concerned about the niceties of the computational complexities or the expressive power or whatever it is that what they're doing, rather than going out there and interacting with industry. So there's an old English I wrote a paper a couple of years ago with my good friend Steve Brooks, and it was called CSP, a Practical Process Algebra, which I would recommend anybody to read who's interested in looking for this sort of approach, right? And in writing that, I came up with two modifications of standard English expressions, right? Which was that one is that too much knowledge is a dangerous thing. That's the standard thing. And what I changed that into too much theoretical knowledge can be a dangerous thing because it can stop you doing things, right? I've actually been talking the last few days for entirely separate reasons with my old friend Scott Smolker from New York, right? And he and his late colleague Paris Kanellakis came up with this sort of completely correct, shall I say, complexity theory analysis of different verification algorithms back in the mid-1980s, right? We showed that CSP refinement was p-space hard, which definitely put us off doing anything for a few years, right? But then because we didn't then understand the fact that just because you're p-space hard or p-space or NP complete or things like that doesn't mean to say you're really hard. It doesn't mean to say that some cases are hard, right? The second one is that necessity is the mother of invention, is another well-known English expression. And I changed this to industrial necessity is the mother of invention, because I myself really care when I'm working with some industrial partners that I can solve their problems. And it was the fact that I was working with an industrial partner who really needed FDR that actually led me to sort of work out the algorithms that work well so much of the time. And so I think we have a lot of the right techniques. It's just somehow we as a community somehow need to embrace practice a bit more than many of us do.
Yeah, agree. Okay. All right. Well, thank you very much. We're out of time, I think.
I mean, like,
you can ask
depends how much time we have, right?
You can ask me later.
A quick one. Yeah.
I mean,
Okay, I have a couple of things I could have asked, but let me pick one of the maybe more interesting ones. Like, you seem to be selling this thesis that basically to perform this, like you want to talk about stochastic certainty, which is basically, you know, with probability at most 10 to the minus a lot, it's okay.
Yeah, that's right. Yeah.
And then after that, you establish this is probably true, and assuming it, you can do deterministic reasoning, and this is extremely powerful, right?
That's right.
Now, one potential problem that many purists will see with this is that in some sense it's compositional, in another way it's not compositional, because in the probabilistic sense, right, it's not really compositional, except the deterministic part composes nicely.
It's made enormously more compositional by the fact that you don't allow any event to happen. If you were actually allowing a few events to happen, the compositionality will really come in and bite, right?
Yes, exactly, because if you would do something like union bounds with 10 to the 100 events, then you would be screwed.
Right, yes, exactly, yes. So I think you've got to be very careful where you apply it. I totally agree with this. One thing I like to use in this connection is what I call the expectation bound on probability, right? So that if you actually look at a random variable, which basically there's a sum of random variables over a huge number of trials, which is 1 if a particular trial comes out to be true and 0 if it doesn't, right? Then it's obvious that the expectation of that random variable is bigger than the actual probability that at least one of them happens, right? But actually, when they're so rare as to practically never happen, the two are actually almost exactly equal. But you simply don't have to deal with these combinations of different things coming in. But